we will go from current slide. Now, the only announcements I know about, and it's not very major, oh, I forgot to mark you here. One is here. That's all that's here, one. Okay. It was sort of a disastrous weekend as far as getting, I mean, I got a lot of stuff done, but nothing school-wise. We had had problems getting in Friday morning and lost about an hour or more getting to campus. And then once there, I had to get ready for a meeting that the dean had called for 12:30. And by the time I got that done with everything else going on that was going on there, then we went to the meeting. It was supposed to be over an hour and a half, and it went way more than twice that long. And so I got home and had no time to do anything there. We were out of town, and I thought I'd get some stuff done there, but I didn't. So all the research papers y'all turned in, I don't have graded yet. Sorry. Oh, wait. That's right. None of them have been turned in yet, have they? Oh, okay. So, don't have to worry about that then. Yes, exactly. All right, but I will try to get the other papers caught up this week, but I have very little time this week either. But anyway, let's go from here. I think we finished this, the one that's on the screen now. That was the example 2. Okay? So, any questions on anything we've done so far? No. Okay. So here was example 2. Here is example 3. It says, revolving about a horizontal axis, find the volume V of the wetting band. Guess you don't have one yet, but I do. Okay. It has a curve on the outside, but also most of the time have a curve on the inside as well. And that's why they call this a wetting band type problem, because it has one curve here and another curve there. Okay? So it says find the volume V of the wetting band in this figure here. Let's blow it up and see what it looks like. I don't think I can get all through. Oh, maybe I can. Look at this. Oh, not quite. So let's just get these done. Okay, maybe that's too high. All right. All right. So what we have here, obtained by rotating the region between the graphs of f of x equal x squared plus 2. Well, that's the one that's curving upward. And because this a is positive, and g of x, which is 4 minus x squared, its a is negative, so it's curving down. Okay, vertex is the maximum. So there's the curve that we have, the area between those two curves, and we're going to rotate that not around the x-axis, but around a horizontal axis, which happens in this case to be y is equal to -3. So you can get the big enough to get around your finger, right? Okay. So, what are we going to do? How will we do this? Well, it's two curves, so we're going to do this area times the circumference, right? This area rotated around the circumference of the curve going around y is equal to -3. So, we'll deal with circumference part later. Let's first deal with that area. Okay? Well, the area here would then be the length, a minus b. In this case, it's g of x minus f of x. That dx then will be the difference between those two times dx, and we'll go either from, okay, they drew the picture for us. We shouldn't depend on their picture. Because guess what? On a test, I'm not going to draw the picture for you. You need to figure it out yourself. So let's first figure out where are the points of intersection. Okay? And how do we find those? How do we find the points of intersection between those two curves? See, they didn't tell you how they did it. They just drew the pictures that there they are.
We have to integrate.
Say again?
Integrate.
Well, you have to know what the limits on integration are. That's what we're looking for. What are those limits? You can look at it and say +1 to -1. It looks like it anyway. How do we get those? And how do we get them from those two things? Set them equal to each other, of course. So you say, so I'm going to have to shrink this. So let's first say, let me get my pen activated because I bet you it's red. Okay. So we say x squared plus 2 is equal to 4 minus x squared. Okay. Proceed. How would we solve that? Add x squared to both sides. Since you're getting everything to the left, go on in, subtract 4 from both sides. Okay? And what does that give us? 2x squared. I can't write. That's a minus. Minus what? 2 is equal to 0. Very good. Now what would you do? Do what? You could, and that probably would work for you, but a little bit safer bet would be, have I asked you what the F word is before? All right, let's do that.
So we factor out of 2.
Factor out of 2, and what are you left with? X squared minus 1 is equal to 0. And that would be 2. Can you factor any further? X minus 1 times x plus 1, and that's equal to 0. And what's that?
That's it.
Well, I need to know what x's are.
You said x minus 1 is 0.
Okay, the 2 you can divide out. Yeah, it's not equal to 0. Not worried about it. So this would be x minus 1 equals 0, or x plus 1 equals 0. What does the first give you?
Positive.
Yes, x equal positive 1. This gives you x equal negative 1. That's how you get those two. Those are the two places where these cross. Where both all the points on there and all the points on here, those two are the two places where they meet. Okay, so you're going from x equal minus 1 to plus 1. And these are parabolae, right? With vertices on the y-axis, right? So I would not do minus 1 to plus 1. I would do twice 0 to 1. Just save yourself a little effort. It's so much easier to plug in a 0 there than minus 1.
So if you go 0 to 1, that means it will be a dx?
Huh?
That means it will be a dx?
Yeah, you're doing dx's here, and they call it x here. I would call this a little, and call this a dx. And the length of that thing is a minus b, and the thickness of it is dx, and then that whole thing, that area then, is going around the axis there, so we'll get to that in just a little bit. Okay? So that's the area of this. A minus B times dx. So the A is this one, and the B is that one. So that would be, okay, the integral from, I'm going to do minus 0 to 1, and double it, right? Okay. Of, and the a here is 4 minus x squared minus the b is x squared plus 2, so that would be minus x squared minus 2, right? It would be b minus a, minus here, both of those, right? So that would be, and then you have a dx, okay? But that's not all, folks. This doesn't give you the volume, that gives you the area of this, right here, 2 times that. You want the volume, so you're taking the area and you're rotating it around this axis here. So what is your axis? I mean, what is your circumference, and what is your radius of that circumference? Okay, not quite. It would be y minus 3. So basically, both of these things are going around. I kind of botched this up, didn't I? Okay. Sorry about that. So it's the radius. This is all right for my area, okay? But the radius, the outer radius and the inner radius, the outer radius is the difference between a and 3, so that would be a minus a minus 3, so it's the g of x plus 3, and the inner radius is f of x plus 3, okay? Because this one minus a minus 3. So that's going to be the difference between those two radii, okay? All right. And that's what the radius around here is. So it's your g of x. This is aggravating. My thing gets all twisted up. Actually, they did show the other. Okay, so let's do the outer radius here, which is 4 minus x squared minus 3, right? No, minus a minus 3, so it's a plus 3, right? And this is your outer radius, RO, and your R inner is your F, which is x squared plus 2 minus a minus 3, so that's going to be plus 3. Okay? Well, this one is fairly easily seen to be 7 minus x squared, and this one is seen to be x squared plus 5. Okay? Now, those are your difference of the two radii. Okay? Now, so take it back, okay? That's now your A minus B, your outer minus the inner. So forget that. Did that one wrong, okay? That would be the area, but you don't need the area yet, okay? I wasn't paying attention to the rotating about the minus 3. So it's 2 okay. Okay. So we have this washer here, the area of this washer. That's what we do first. I was doing the area of the whole thing first. We do the area of this washer first, and then do the dx here. So the area of this washer is the outer radius minus the inner radius, the area of the outer circle minus the inner circle. The area of the circle is pi r squared, right? So that would be pi times this thing squared minus pi times the interval squared. And then your dx is going to do it over the whole wetting band. And so there'll be 2 times pi from the area, pi r squared, and then you have the outer radius squared, so that'd be 7 minus x squared squared minus x plus 5, x squared plus 5 squared. Okay, that gives you the total volume. So you do the area of the ring here, the washer here, that's the ring, the washer here, and integrate that, double it from 0 to 1. Okay, that's what we're going to be doing. Don't start with the area there and do it. You do the outer minus inner of actually what you're doing. So that's a bigger circle than if you had done it from the x-axis. Okay, so it's the outer minus the inner, and then integrate that, double it from 0 to pi. Well, the radii, the area is pi r squared, so that's where it's not a circumference that you're dealing with. It's the area of that washer from 0 to 1, and double that. Okay. Sorry, I got you off on the wrong foot there. Let's first do this square. Okay. What's 7? Well, I'll just do it here. Woo. Okay. Let me. We've already used these. I need the. Well, I'll leave them for now because we do have more room. All right. Let's carry this on down here. Okay. This will be 2 pi times the integral from 0 to 1. The 2 is, I say 0 to 1 and write 2 because I was, the 2 is because we're doubling it, what it would be from minus 1 to 1. The pi is from the area of those circles, and they're common to both. The pi is common to both. So what do we get when you square that first one? That. Second? I couldn't hear.
49.
49
Minus x.
Minus what?
X.
Second? Okay, yeah, you left off the inner terms, the cross terms. Okay. Not 7x squared. Twice it. 14x squared. No, yeah, 14x squared. And then what you said at the end. Say again. Okay.
Oh, x.
X, and what sign? Plus, yeah, because he's squaring a negative. Okay. Okay, x to the 4th. Okay. All right. Minus, I think I'll leave it in parentheses because I'm afraid that would be too many things to try to keep up with. So square x squared plus 5. What does that give you? Got it? Plus. I don't think so. 10x squared. Plus 25. Okay. And then that's dx. Okay? Now, if it's all right, I'm going to remove the parentheses and change the signs of everything inside. Is that all right? Because I just don't want to write it again. Okay? So I'll remove that parentheses, leaving a minus x 4th That'll make a minus 10x squared minus 25. Okay. Now, from that, you see you have a plus x to the fourth minus x to the fourth. Thank you very much. They go away. Okay? And what does that leave you with? Let's write the integral down here. Is equal to 2 pi times the integral from 0 to 1, 49 minus 25. What's that? $24. And then you got a minus 14x squared minus 10x squared. Minus 24x squared dx. Ha! What do you notice you can do there before you start trying to do an antiderivative? Huh?
It's not substitution.
Something pretty simple.
Oh, factor.
Ah, yes. Factor out of 24, so you don't have to carry around those big numbers. And that will be a 48 pi now times the integral from 0 to 1 of 1 minus x squared dx. Okay, I think you can integrate that, can't you? Antiderivative of 1. X, okay.
Minus x cubed
Over 3. Evaluated from 0 to 1. Okay. That'll be 48 pi times
1 minus 1/3.
which is
2/3.
2/3. Okay, will 3 go in the 48?
Oh, yeah, 16.
16 times. All right, you got it?
Yeah.
Did you get that too? Kinda. Well, 3 will go in the 4 one time, 1 left over. 3 will go in the 18 6 times. All right? Okay. So what does this give you? Is what? 16 times 2 is? 32 pi. Okay, that should be the volume of that wedding ring. Okay, let's see what they got. Oh, there it is. Yeah, 32 pi. They got it too. Good for sale. See how that works? Okay. I believe this may be the first day Bailey's missed. I guess he's not going to make it in. All right. So that was that one. Ready for example 4? Okay. Find the volume obtained by rotating the graphs of f of x equal to 9 minus x squared. Let's see if that's here. Okay, there's f of x equal to 9 minus x squared. And y is equal to 12. Y is equal to 12 is right here. Okay. And it said, find the volume obtained by rotating those graphs about the A part, the line, y is equal to 12. So this time you're going to rotate this around the upper boundary. So you're going to have what? to have a little disk because there's no gap in there. Okay? Forget about this 15, that's the B part. It's rotating this about the line y is equal to 12. So you have a megaphone, you know, but it's nothing, it's a solid megaphone, so you can't yell through it. Okay? So that's what you get. Okay? So how are we going to do that? What's your outer radius on this one? Well, when you do your dx's here, I prefer a dx at x there. Okay, but let's do it here. Whoops, I'm going to have to shrink it to do this. So I'm going to have a dx here, and this will be a dx here, and this is a little plate, okay, a thickness dx. And what's the radius of that plate? Okay, it would then be okay, yeah, okay. It is 12 minus 9, but yeah, so yeah, that'll be the radius. You want the radius to be positive. It's not going to matter, you're going to square it anyway. So 12 minus 9 minus x squared, that would be what? 12 minus this would be yeah, 3. 12 minus 3. Huh? It's 12 minus this entity here. 12 minus 9 would be 3. It's a minus x squared. Yeah, plus x squared. So 3 plus x squared is going to be the radius of this thing. Okay? And that's just a disk. So that would be the integral from, oh, I didn't read the whole problem, did I? For 0 less than or equal to x less than or equal to 3. So 0 to 3. Pi, because pi r squared, and your radius would then be, what did we say it was? 3 plus x squared was the radius, right? Squared. And then do that by your dx, and that gives you your total disk. The summation of all those disks. Okay? Let's go on and do that. That would be, let's maybe keep it here. Pi times the integral from 0 to 3 of, can you do that? Square that binomial. Is what? Okay. Right. Plus 9. dx. Okay, can you do that antiderivative? Over. Right. By the x to the third, 2x cubed. Okay, got it. Evaluated from zero to 3. Okay, now the calculus was easy. The math is hard. I mean, it's definitely messy. Okay, 3 to the 5th. Wow! The 10 o'clock scholar. Okay. We were just saying this is the first day you had missed since she started coming. So. Oh, really? Oh, man.
Yeah, right there at 280. Past 280. 65.
Uh-huh.
There was 3. My brother said it was an 18 wheeler, but I just saw 3 cars that were torn up and they had all the lanes closed.
Wow.
I actually left early this morning.
Oh, really? So you don't have a class on the Birmingham campus before this? No. You just, oh, no, you don't. UAB before this. Yeah. You just come here first. Okay. Oh, sorry. I told you I was late Friday. I was involved in something like that on Friday. I was an hour plus getting to campus on Friday morning because of something like that. It wasn't that major, but it was, it can sure shoot a hole in your day, can't it? Yeah. Okay. We're doing example 4 on page 354, chapter 6, section 6.3. And Juan is really upset you're coming because he was so much enjoying answering all the questions. Yeah. So he's really mad at you. He won't say it. He's a nice guy, but he's ready to shoot bullets at you. Okay. All right. All right. So here we're doing, the calculus was easy, fairly, but now we got to evaluate this. So 3 to the 5th power. Anyone know about what that is? Oh yeah, you got calculators that can do it. But anyone know what 3 to the 4th power is? About 3 squared.
3 squared is 9.
Okay, and then 9 squared is?
81.
81. So that's 3 to the 4th. So multiply that by 3 and you get 243.
Oh, okay.
Yeah, those calculators slow you down, don't they? Okay.
I had to record it. I was doing that.
All right. But isn't that right? Is that what your calculator gave you finally? Yeah. Yeah, right. 243 over 5. Really? Did it? Did you actually do it? No, it's 3 to the 5th power. All right. Good. All right. Plus, we all know what 3 cubed is. 27 times 2 is 4. Okay. All right. Plus 9 times 3 is? Second? 27. Very good. All right. Now, the only thing is you got to get everything over 5. So it's 243 fifths plus, yuck. Okay, how many fifths is 54? 230? 270. Okay. Yeah, you're right. 270. And then, how many fifths is 27? Oh, you calculated so you don't know. 135. Easier way to do that? Isn't that exactly half of 54? Right. Huh? Okay. Now we got to add those together, which is fun too. Okay, that looks like about 648. Is that right? Nice round number. No, it isn't. Oh yeah, I looked at the wrong one. Yeah, 648 pi. I thought you were from Springville.
That's from, we moved to Pell City.
Oh, you did? Okay. Okay. Are you still coming 280? I mean,
I go I-20,
oh,
then get on
459 and go around.
Yeah.
Okay.
I mean, I can go either way, but I didn't know there was a red.
Didn't know there was a right
Until
to it.
I was pulling
All right.
I live in X with 459, and it's like 459 is just like prone for like accidents. It's like every time, like when I used to work at 280, I always be late for work. So there's always something.
Right.
And then last semester, I had a history class at Jump State, and I was late by like an hour and a half because there was like an old truck.
Right.
No, 459.
Yeah.
So
When I was drinking this, I taught as an adjunct at the Jeff State, the campus down in Shelby County, the Shelby campus of Jeff State, and we lived in Southside Birmingham. And one day I got down, I was early, like you were, and I got almost to Valleydale Road. Didn't quite get there. There's first 459, then Valleydale Road. When I got within sight of 459, everything prepped to almost, they had a big oil tanker or something like that spill and shut down all of 459. So they were rerouting everything to Valleydale Road. Well, I got there, it slowed things down. I got within sight of the intersection of Valleydale Road, within sight of it, at the time my class was supposed to start, okay? And I crept an inch at a time, getting on it, and by the time I lost the intersection in my rearview mirror, my class would have been over with. So I was an hour and 15 minutes getting from where I could see Valleydale Road intersection to where I couldn't see it. An hour and 15 minutes sitting there going along like that.
Like Valleydale Road is that it's a one lane street.
Yeah.
So like all the traffic just backs up.
Yeah. So you're right. Everything happens. I mean, a lot of things happen there. They used to call Malfunction Junction the malfunction, but boy, 459 is really trying to rival it. Okay, so that was the A part of this problem. The B part said rotated about the line y is equal to 15. So again, we're going to take this curve here, bounded by f of x is 9 minus x squared. And by the way, why did they stop at 3? They didn't tell you you had to, but they did stop at 3, thank goodness, because if you had gone down here, it's like if this had gone to 4, then it would have still been R. It would have been okay. You just would have had to worry a little bit more about it, but because you're doing the length of that, that would be 12 minus a minus number, that would be fine. So you don't have to be above the y-axis, but they chose that so you could. It doesn't bother the problem anyway. Okay, this time we're doing that same area around y is equal to 15. So this time we have the Christmas tree stand here. Real small Christmas tree, right? Okay, so again you do your dx. They just say x. I like to say dx here. Just do a little dx here and make this a real washer with a thickness to it. I can't draw, but you get the idea. And what's the area of the washer? Well, it's the outer radius, pi r squared of the outer radius minus pi r squared of the inner radius times your dx. That was be the thickness of the washer. And that's what you integrate from your x going from 0 to 3. So that would then be pi times, well, let's do the integral. Okay. And again, that dx, the x is going from 0 to 3. That doesn't change. But what's now your outer radius? Here is this is your function down here. Okay. The outer radius is from that line to here. What would that be? We stated wrong the function in here, or stated it. F of x is equal to 9 minus x squared. That is this curve right there. Second? Okay, so it's 15 minus 6, minus 9, which would be 6, plus x squared, minus a minus, right? Okay. All right, so the outer radius would then be, you got your pi on the outside, and you said 6 plus x squared squared minus, that's the outer radius. Your inner radius is 3. I see you look at that. Yeah, it's 3. So 3 squared is 9. Okay, so that would be minus 9. And then all that times your dx. Okay, and that will give you your, this is the washer method. Okay, so again, 0 to 3. Let's square that one. So we come up here and square it. Just save ourselves some effort here. What's the square of 6 plus x squared? X to the 4th. He'd like to do it backwards. That's fine. Plus 12x squared. Plus what? 36. And then you're going to subtract 9 from that, and that would leave you 27. Okay, so that's what we're integrating here. Pi times x to the 4th, well, not yet. That's the first part of it. Plus 12x squared. Goodness gracious, it keeps doing it. Plus 25. Okay. Okay, well, that is all you got. Okay. 27, I'm sorry. (27) dx. Okay, so let's do the integration. What would that be? Help me, help me. X to the 5th over 5, that's the same as before, plus 4x cubed plus 27x. Okay, evaluated from 0 to 3. So this will be your pi times, and we've already done that. That's 243 fifths. Okay, plus. Now, we had 2x cubed before, so this would be just double that. 108, right? By that. Okay. And then 27 times 3, I think we know what that is, don't we? Right? Okay. Now we got to get all those to fifths too, so this will be pi times 243 fifths plus, and that would be 540 fifths, right? Okay, plus, and this will be, say again, 405? Yeah, 405 fifths. All right, a little bit bigger numbers here. Let's see what that gives you. There's your pi. Let's see. 540 plus 405 would be 945 plus 243 would be 1188. I think that's right. 1188 fifths. Okay, or I think they write it as 1188 fifths pi, or something like that. Okay. And that's exactly what they got. Good for them. All right. Make sense? All right. Now, can you do something similar with vertical axes? Why not? Okay? And this problem will be like that. Revolving about a vertical axis, find the volume of the solid obtained by rotating the region under the graph of 9 minus x squared. That sounds a lot like what we were just doing, wasn't it? It was, but notice how they... I really don't like it when they do this. Here's 9 minus x squared here. And notice that this is 3 and that's 9. So they've really compressed the y scale and expanded the x scale, because that doesn't look anything like the parabola we're doing. It doesn't matter what it looks like, the integration is the same. Whereas on this one, when they're doing it, they are not even, they're closer to reality. That's 3, and that almost looks like, this is a little bit more. So again, they still compress the y scale with a little bit expanded x scale, but not as badly as we did before. Okay. But if we're doing revolving around the y-axis and we're doing the disk method, and what axis are we revolving around? I need to read the whole problem. Find the volume of the solid obtained by rotating the region under the graph f of x equal 9 minus x squared, which we got here, for 0 less than x less than 3, we got it, about the vertical axis x equal -2. So this one over here, if we're going to use the washer method, then what is our d's? What is the incremental parts? Second? Well, I'm not looking for a number. The increments is dy's now, right? So you have a dy here. Rather than just y, make it dy. Let me clear up some of my scratch here. Well, that was okay. That'll be a dy, not just a y. I like to do that. So that's the thickness. But if you're integrating over dy, that means you have to get this as a function of y, not as a function of x. So how do we do that?
0 to 8, or no, 0 to 9 minus 8.
Okay. All right. Okay. Wait. What we're trying to do is get this expression in terms of y, not in terms of x. If you're doing a dy, you can't integrate with respect to x. So how do we get that to be in terms of y? Solve for x. Okay, solve for x. And what would you do first? Say again?
Subtract 9.
Okay, you could do that. Subtract 9 from both sides, and that gives you y minus 9 is equal to negative x squared. We want to solve for x, so what do we do? Okay, and what would that give us? X squared is equal to
-y plus,
which you could say is 9 minus y, right? Okay, and then take a square root. So x is equal, and most of the time when you take square roots, you do plus or minus. But so you see here, all your y's, your x's are positive, your y's are positive, so I think you can get away with just the positive square root of 9 minus y, right? Okay. Now, that is your x as a function of y. Okay, so this curve is now x is equal to the square root of 9 minus y. Everything's the first quadrant, so everything's positive. Okay? But that's not your radius. Okay? That's just your curve. What is your, if you're doing the disk here, I like to just go into this figure here. Here's your dy, and you're going from, and this is from -2, so this is your dy here, and you're doing that around there. What's your outer radius? Our outer would be, say again? It would be this x here, which is the square root of 9 minus y minus a minus 2. Okay? So that would be plus 2. Okay? And your inner radius is what? 2, yeah, because it's from -2 to 0, which is 2. Distance of 2. Okay? And it's a washer method, so we're doing your volume would be pi, because of pi times the r squared of both of those. And your y's are now going from what to what? To 9, yeah. Okay. 0 to 9. And your outer radius, you're going to square it, because you need to square that. What is that thing squared? Want to do it up here? We can. 9 minus y plus 4. I'll buy that. Is that all? Square a binomial. Square the first. Got that right. What else? You square the last. You got that right. What goes in between? Double the product of these two. So that would be plus 4. Double 4, yeah. 4 times the square root of, so we got another plus 4 times the square root of 9 minus y. Okay. Big boo hiss, right? Okay. What do you get when you square the inner radius? 4. Okay, that's a lot nicer. Okay. And it's the outer radius squared minus the inner radius squared, which is this 4 subtracted that 4. You're done for, right? So this will be 9 minus y plus 4 times the square root of 9 minus y dy. I'm not sure I like this desk method very well, do you? Okay. It works. But how are we going to do that? Say again?
Change the 4 times radical or square root of 9y to 9y.
Okay, yeah, I'll definitely do that. But here's the other thing I suggest. Let's go and split out and do this part. 0 to 9 of 9 minus y dy. And then do a plus 4 pi times the integral of, and like you said, do a 9 minus y to the 1/2 dy. Now maybe you don't like doing it that way. You don't have to, okay? It's perfectly fine. So how would you do it from there? Oh, I forgot to put my limits in there. 0 to 9. I like doing it that way. I mean, you could have kept it all together. I just found it a little easier to split those out. Because I can do this most of the time. Okay. What would that be? Evaluated from 0 to 9. We'll come back and do that. What would you do here? And you might could have done it all together. It sounds like you probably could have. What would that be then? Since you wanted to do it this way, what would it be? How would you do that? So times 2/3, is that what you said? Right. At all? Because of the chain rule, you're going to need a minus sign. You see that? You may not see it. It's okay if you don't see it. Okay. Okay. That's why I hesitated doing it this way. Because you do have that added little step in there, okay? Because you're taking the antiderivative of this, but when you take a derivative of this, let's do it. That'd be 3/2 times 2/3. Forget that minus sign. That would be 1 times this to the 1/2 power. But derivative, you have to have chain rule, you have to do a minus. So since you have a minus in going that way, you have to have a minus this way. If you don't see that, then try this. This is what I thought you were going to do until you said that. I said, I bet you's not going to do it that way. Let's let u equal 9 minus y. Good old substitution, right? Then du is equal to, whoa. Okay, just taking a derivative. Minus dy, right? Just taking derivative of this side would be du, derivative of this would be 0, derivative of that would be minus dy, right? Got it? Okay. So then dy would be minus du. So you could move the minus sign over here. Okay, then it would be 4 pi times the integral. I'll leave off the units for now. And that would be u, put a minus sign out here, u to the 1/2 du. Okay, now let's get, then we would need to get the units in place and stuff like this, but you see the minus sign shows up there. Okay, so if you don't put the units there, that'd be a minus 4 pi, and this would be u to the 3/2 times 2/3, so it'd be 2/3 u to the 3/2. Okay, that would be correct that way, but you see the minus is there, and that would be minus 8/3 pi u to the 3/2, but then plug this back in, it'd be 9 minus y to the 3/2. So you see you do wind up with a minus in front from your substitution, but you also get it here if you did that, because you're integrating with respect to y, you have a minus y, so it introduces it. And see, this gives you the same thing as that. Do I convince you? Or confuse you? Okay, all right. Okay. Now we got to evaluate that from 0 to 9. Okay. So this is going to be a pi, and what do you have here? 81. 81 halves, right?
Yeah.
Oh, you already did that. Okay. Okay. We'll come back and do that in a second. I'm going to put a minus here. Minus 8/3 pi. I pulled the 2/3 out with that, okay? And then this will be what? If you pull all these things out here, that gives you minus 8/3 pi. Okay, so now we're just doing the blue part. So plugging in 9 here, what do you get? 0. Okay, I could have done that. Okay. And then you plug in a 0 there, and it's minus this. Okay, 9 to the 3 halves. What you want to do first? Cube it or take a square root first? That's what 3 halves mean.
Yeah.
Right.
Square root first.
Yeah, take square root of 9 is 3. And then cube that, 27. But that would have been a minus, so this minus here becomes a plus. So this would be a minus 27. Okay. Because the first one was 0, the next one was 27. So that gives you a plus, and 3 will go into 27 9 times. So let's see what we've got here. The first part gives you 81 halves pi, because 81 minus 81 halves is 81 halves, right? Okay. Plus, what did I say that was? 72 pi. Boy, that seems like it's way too big. Maybe not, though. Okay. And this would be 81 halves pi plus 144 halves pi. So that would be 225 halves pi. Is that right? Oh, look at that. I got it right. Okay. A bit on the messy side, right? But doable. Okay. Lots of little things there. Those minus signs, they really like to sneak in there and screw you up, don't they? Okay, so you have to be really, really careful. I mean, here you had another one. You had a 0 minus of this, and that came out to 27. You had to remember it's a minus 27, but then you had a minus here and a minus there, so I shouldn't have put that to a plus. So anyway. Yeah, it certainly could. All right, but 225 pi. Well, that ends 6.3, which is basically the volumes of revolution, basically by the disk and washer methods. Okay, how about 6.3? Do you want to do? Whoa, okay. This is a summary here then. Okay. This is showing you all the different. Ooh, that's not what I want. No. So aggravating. Oops. There. Hit the wrong people. Okay. Here's if you have a function of x, or the x-axis revolved around the x-axis, rotated around the x-axis, you just do a disk. You imagine that revolved around here. You got the volume of the disk is the length times the width, the area of the disk, which would be pi times the r, which is alpha of x squared, times the dx, and that gives you volume. And that is revolved around the x-axis. If you have a difference of two functions revolved around the then is the outer one. It's the area of the circle of the outer one minus the area of the circle of the inner one, which basically is the area in between, which is the outer radius minus the inner radius, but they're both squared, alpha of x squared minus g of x squared times pi, and then times dx, and that gives you the value there. If you're rotating about something else, then especially if the y is equal to c is up there, then your outer radius is now the g minus, or c minus g. The inner radius is c minus f. Whereas here, f is the outer radius because you're revolving around something below it when you're something above it. There's your outer radius, and there's your inner radius. So you just have to keep up with which is out and which is in. This time you have the y is equal to c below it. So, and this time this is above the x, so your outer radius is f of x minus c, okay? And the inner radius is g of x minus c. If your axis of rotation was down here, it would be f of x minus a minus c, which would be a plus c. G of x minus c would be a plus c. So, they only showed a few of those, but man, the only thing that has to happen is your axis of rotation can either be the axis itself, something parallel to the axis but completely below the area, or completely above the area. That below the area can be positive or negative. The above is of course always going to be positive, but whatever you do, figure out what your outer radius is minus your inner radius is. Okay, now, I guess this is going to give us about as much room. You want to do the preliminary questions? Yay or nay? What you think? Yes or no? What you think? Sure? Okay. Which of the following is a solid of revolution? The sphere? So like a baseball? Is it a solid of revolution?
What does it mean by revolution?
Okay. It means we're coming up in arms against the dictators. No. It means we're revolving it around something.
Yes.
Yeah, it is. You take a semicircle and revolve it around its base, you get a sphere. How about a pyramid? No, that wouldn't work. A cylinder? Yeah, that would be. How about a cube? No. Okay. So that should be a yes, no, yes, no. Okay. This is 6.3. Oh, it's not on the page. Oh, A and C. Okay. Which of the following is a solid? A and C. Yeah. True or false? When the region under a single graph is rotated about the x-axis, the cross-section of the solid perpendicular to the x-axis are circular discs. True or false? True. That sounds true to me. Let's see what the book said. True. Good for them. Okay. Number 3, true or false? When the region between two graphs is rotated about the x-axis, the cross-section of the solid perpendicular to the x-axis are a circular disc. What you think? Yeah, but this is two curves now, between two curves as opposed to one curve. Is that a circular disc still?
Yes.
They're circular washers. Yeah, you got a hole in the middle. Okay? So I think that should be a false. Let's see what they say. False. The cross-section would be washers, not discs. Number 4. Which of the following integrals expresses the volume obtained by rotating the area between y is equal to f of x and y is equal to g of x over a to b around the x-axis. Basically, we're talking about B here. Okay? Wouldn't that be it? Okay? So which one would be that? You say B. And why do you say that?
That's the correct form to write it.
Yeah, because it's the outer radius squared minus the inner radius squared, not the difference of the radii squared. You're right. It's B. Very good. Okay? All right, B. Good for you. Okay, homework exercises. Either 1 or 3 or both. Any of the odds 5 through 11. Do 13. Any of the odds 15 to 19. Either 21 or 23 or both. Do 25. Any of the odds 27 to 31. Either 33 or 30. Oh, I'm sorry. Any of the odds 33 to 37. There's some hints in there that threw me off. Any of the odds 39 to 51. And then I would say any of the odds 53 through 59. All right. There may be something you'll find in there that might be suggestive of a paper topic. I'll let you decide on that. So, no more questions there? Oh, that's not what I wanted. All right. All right, let's move on to 6.4. Now that last one we did, which you had to change to y as a function of x, to x as a function of y, and then you had square roots in there and all sorts of things that were sort of weird. I think we'll find there may be an easier way to do that. Okay? Let me get the slideshow set up from current slide, and we'll go from there. Now, they're first going to show you a generic, why is it doing this? Okay. All right. This is a cylindrical shell. How would you determine its volume? And this is approximate. It's not an exact thing. Okay? Well, what you do with the cylindrical shell is, if you want its volume, would be, let's take some tin snips, okay? And snip up one side, okay? And then lay it flat. Now we have a what? Okay, this can go up perpendicular to the thing and then flatten it out. What do you have? A rectangle. With a thickness, what was your thickness? Delta R, change of radius here. Okay, that's outer radius minus inner radius. Capital R minus little r is your delta R. That's now the thickness of that rectangular solid. And then you have the length times the width. Well, the width is 8. What's your length? The circumference of that thing. Circumference is 2 pi r. That's the, whichever one you want. H is the height, and delta R is the thickness. Okay? What's that?
So it would be like base times height times length?
Yeah, times thickness. You're absolutely right. So, whereas the length is, the base is 2 pi r, the height is h, and the thickness is delta r. Now, what I haven't figured out is why wouldn't they say little r dr? Why capital R dr? Either one of them, but why choose the one that's not this? It really should be, I think, little rdr, because that's what it's going to be from now on. So it's sort of like capitals R at a constant. It's not. It's just one of the radii. So what if you use the other radii that's the same as this? Or else call this delta capital R1. I mean, I wouldn't mix the symbols like that. But they did. But it's beside the point. You can follow that. And that gives you, and this is exactly, I think, what one was saying, or one of you was saying, never mind, is the volume of the shell is 2 pi the radius, okay? See, I'd like to put in radius in there, then not capital R, times the height, h, times the thickness, dr. So 2 pi r, h, dr. Okay. Good deal. Now, what if you have a curve like this that you're rotating around the y-axis, not the x-axis? X-axis wouldn't have been too bad, but you're rotating this around the y-axis. Okay? Now, this curve here from A to B, rotating that around the y-axis. Okay? Now, if you knew x is a function of y, then you could do the disk method and do dy's. Okay? But then you have to know what this value is here, c, and this value up here, d. We don't know either of these, and we don't even know that this function can be written as x is a function of y. So let's use what we just did, the shell method. Okay? Now this time, before, they just said x, and I said I like to think of it as a dx. Well, now they do a great big dx, x of I minus 1 to x of I. I would make that a little smaller and make it a dx. And then it's this area times times its circumference, okay? And that will give it to you, okay? And then you integrate that from here to there, okay? Well, what would this area be? It's this length here, okay, times and that basically was your height before. Okay, what we used is h before, and your dr, this is your dx now, and then the 2 pi r, that would be 2 pi x. So your radius is from here to there, that would be x. So 2 pi x dx times f of x. Okay? Now, showing the same thing here. It's the area of this shell, ice shell here. You break this into, okay, this is going from A to B. This one they're not showing that going from A to B, okay? So forget about that part of it. Because if you were, you just have a little cylinder in the middle, but you don't have to worry about it. They're showing this if you're going from 0 to B, okay? And this ice shell would be your length, which is 2 pi x. Okay, x is your length out this way. So 2 pi x times the height, alpha of x, times your dx. We were saying dr before it, dx now. So that gives you exactly what we have here. Okay. Okay. This time they do show this. So you're going from A to B, and you're just doing this. That was just showing this one little segment here. So you're going from A to B, and that's your x's are. You're going to be at this area, which is length, which is your alpha of x. Two pi x, because this is your radius here, 2 pi x braided strip rotated about the y-axis generates a thin shell, and you integrate that all the way around. Okay. Now, this is showing if you have multiple thin shells. The first integral you do, if you did this is going from x equal a to b, okay? And if you had pretty thick delta x's, then your d high, whatever this looks like it is here, kind of like a hockey puck with a hole in the middle of it, but that would be your curve. These would be estimates of that curve. If you want a better estimate, do it a smaller dx, and a better estimate than that is do even a smaller dx, and as you get smaller and smaller dx's, you get closer and closer to being exactly what that is. The cylindrical shell approximation as n approaches infinity. When it does get to infinity, you've got a smooth curve. Okay. So I think this may be, this is the first problem. The funny thing is they should have the formula before the problem. So let's show the formula. Sometimes whoever put the slides together got them kind of out of logical order. So this is closer to that. Volume of a revolution of the shell method, the solid obtained by rotating region under y is equal to f of x over the integral x equal a to x equal b, those are your own x's. About the y-axis, though, you can't, if you do the disk, you have to do dy. So you have to get this in terms of x in terms of y, and you have to know these along the y, which you may not know right off the top. Okay? But that would be 2 pi r, that's your length basically of that flat shell, times the height of that shell, which is your f of x, so 2 pi x, f of x, and the thickness of the shell, dx. Length times width times thickness. Okay? You got it. So, let's go back one, and this is example 1, I believe it is. Okay. Find the volume V of the solid obtained by rotating the region under the graph. F of x is equal to, there it is. Blow it up so it's easier for you to read, perhaps, but we're going to be shrinking it back down as soon as we start writing. So f of x equal 1 minus 2x plus 3x squared minus 2x cubed. Okay? Rotating that region by the value of the solid obtained by rotating the region under the graph of that over 0 to 1 about the y-axis. Okay? That is really a strangely put together sentence. They have so many prepositions and the order doesn't seem quite to be right. Find the volume of the solid obtained by rotating under the graph over this about that. Okay? But you get the general idea. Okay? So let's do it. Okay? And again here, I like to think of this as a dx. Okay, let me go and shrink this down and get my pen dark again. Think of this as a dx. Okay? So, what is the volume of that cylindrical shell? Okay, you tell me. Two pi, and 2 pi goes part of what? Say again? Okay, it's going 0 to 1. Two pi what? X, exactly. The function, which is 1 minus 2x plus 3x squared minus 2x cubed times dx. That's the thickness, finally. Okay? What do we need to do first? Let's distribute. And what does that give us? X minus 2x squared plus 3x cubed minus 2x to the fourth dx. All right, can you do that integration? Antiderivative. X squared over 2 2/3 x cubed. Very good. 3/4 x to the fourth x to the fifth. Evaluate that from 0 to 1. And this isn't too bad of an evaluation. Next part will be a little nasty, but this isn't bad. That'd be 2 pi times 1/2 minus 2/3, 3/4 minus 2/5. That was easy. Now getting it into a coherent answer, 2 pi. What do you do first? Let's say again. Say again. Okay, you. Say again. What are you looking for? Common denominator. What would it be? Well, think of your prime numbers here.
120.
Yeah, 20. Okay. It would just be, no, I'm sorry. Okay, you said 120. Okay. Think of your prime numbers. 2, 3, 2 by 2. Well, this 2 is already counted in 5. So basically the product of these. 15 times 4 is 20 times 3 is 60. 120 is a common denominator, but it's not the least common denominator. You could use it, but if you're lazy, you like to do the least one because you have less work. But hard workers can still do it. Okay. Lazy people have an advantage. So your common denominator is 60. How many 60ths? 60ths is 1/2. 30. How many 60ths is 2/3? 40 60ths. How about 3/4? Say again? 45, okay. And how about 2/5? How? Say again? 50? 2/5 should be less than 1/2, right? Huh? I can't hear. 24, yeah. All right, okay. Second? Yeah. Okay. Now, I like to add the positives together. That would be 75 60ths minus 64 60ths, which would be and you multiply it by 2/3. Why didn't I do? I mean 2 pi. So that'd be 11/30 pi, I think. Oh, look at that. They got it right. Good for them. Okay. Make sense? All right. Now, little bit of what they call conceptual insight here. I think that's what they show here. Okay? This isn't a particular problem. It's just what they're talking about. If you're dealing with shells or discs and you're having to decide which you want to use, here's the deal. For a rotation about the y-axis, the shell method uses y is equal to f of x because you're using a dx there to be the thickness of the shell. But the disk method, you're having a dy here. To get a disk out of this area of the disk, you use a dy, so then you have to change the y is equal to f of x to x equal g of y. Okay? Now, some functions that's easy to do. And if it is, go with whichever one you like better. Okay? But some functions are almost impossible to change the variables. Okay? And are really messy. So if you don't want to go through that mess, use the shell. Okay? So they say a little bit more in that. But when you're using the shell method, the shell height is always parallel to the axis of rotation. When using the disk method, the radius is perpendicular to the axis of rotation. So see whichever does best. All right? Now, what if you had a disk that was going, a shell that was going between two functions, not to the x-axis, but between two functions. Then your 2 pi r, 2 pi x, or 2 pi whatever, yeah, there's an x there, a dx there, this is going to be an x here. So 2 pi x, whatever the radius is, and that's x in this case. The height of the shell now is just the difference between those two functions. Okay? And then your dx is just like it was before. So basically, nothing changes about your formula, except that rather than f of x, you have f of x minus g of x. Okay? And guess what? There's no squaring of those things, so you don't run into big powers. It's just a difference of those two. Does that part make sense? All right. I think we're ready for this one. Are we going to have time to do this one? I kind of doubt it. Okay? Do you think we would be able to? Y'all feel really quick today? So let's stop there. Page 361, we'll pick up with example 2. Okay? We made decent progress on 6.4. I think you can do any of the odds 1 through 5. I think you can do any of the odds okay. Let's just stop at 1 through 5, because the rest of those is it's between two functions, and since we didn't do an example, we told how to do it, we didn't do an example. You can hold off on that. Okay? Now, let's look a little bit into the future, crystal ball time. We've got 6.5 to go, and 6.5 is not that long of a section. There is a fair chance that we will finish 6.5 next time, which means if I can remember to do so, I'll have your test ready for you. And your test will cover wherever the substitution method was that 5.6 or 5.7, somewhere back there in Chapter 5, that one section in Chapter 5, and these 5 sections in Chapter 6. So basically you'll have 2 questions from that substitution method, and then 2 questions each from each of the 5 sections here. I'll try to have that ready for you on Wednesday. I know y'all have been chomping at the bit wanting to get a test. That's why you hurried up and got your papers done while you didn't have any tests to interfere with that. Wasn't it? Okay. And so now you got papers and tests due. So blown your free time. So now you got both of them to look forward to. So we'll pick up and go from there. All right, good deal. Did I cheat you out of any tuition dollar? Came close, but maybe not.